Hi, my name is Ashish and I'll be presenting our work aligning non-causal factors for transformer-based source-free domain adaptation conducted at the Vision and AI Lab at the Indian Institute of Science. Domain adaptation is the ability to adapt an algorithm trained in one or more source domains to a different but related target domain while reducing the domain gap. A more restrictive and privacy-preserving variant of this problem is source-free domain adaptation, where a vendor trains a source model on their proprietary data, which is both large-scale and labeled. The vendor then shares this source trained model with the client for adaptation. For domain adaptation, a model requires learning of two types of factors: the causal factors that represent the goal task related features and non-causal factors that represent the domain related features. Conventional domain adaptation algorithms only focus on the causal factors for domain invariance. However, this results in suboptimal alignment of the class-specific clusters, especially in the case of large domain gap between the source and target domains. We find that there exists a spurious correlation between the causal and non-causal factors, which breaks when a domain shift occurs. Therefore, we aim to preserve this correlation by aligning both the non-causal and causal factors for effective adaptation. Aligning the non-causal factors leads to an overall global alignment between the source and target domains. In other words, it implicitly improves the alignment of causal factors as well. We develop a transformer-based framework for source-free domain adaptation called Causality-enforcing source-free transformer, which comprises three steps. First, selection of the non-causal attention heads for the style task. Second, non-causal factor alignment. And third, task-discriminative causal factor alignment. Before we select the non-causal attention heads, we create the style characterizing inputs used for this step. We first take the dataset and create augmentations to simulate virtual domains. To preserve only the non-causal factors, we apply the task-label destructive transformation of patch shuffling. These specially constructed inputs are then used to determine the importance score of the attention heads towards the goal and style tasks. In the first step, we estimate the causal influence score of each attention head in a given transformer block. This is done by training convex weights beta 1 and beta 2 that combine the output of the attention heads for the normal input and the style characterizing input. A higher value for beta 2 indicates that the attention head gave more importance to non-causal style factors and can be chosen as a non-causal attention head. Once we determine the causal and non-causal attention heads in the model, we train the style classifier and the non-causal attention heads via the style classification laws shown here. In this way, the non-causal factors are captured by the non-causal attention heads while the causal attention heads are frozen in this step. After the second step, the causal attention heads and the task classifier are trained with the goal task classification loss while the non-causal attention heads are frozen. This ensures that the causal factors are disentangled and learned along with the non-causal factors. In summary, the vendor first trains the source model with the source domain loss using all the steps from our proposed framework. The client follows the same steps with the target domain data by replacing the supervised task loss from the source side training with the information maximization loss. With the DEIT B16 model pre-trained on the ImageNet dataset, our method achieves state-of-the-art results on the Office Home dataset, outperforming prior works by at least 2%. Notably, we achieve similar results to the non-source-free prior work C-SFTrans. We achieve similar improvements on the Office 31 and Vista domain adaptation benchmarks. We also outperform prior works on the challenging multi-target domain adaptation setting, where the model is trained on a single source domain and adapted to multiple target domains. For the sake of time, we have shown a highlight of the results of our proposed framework. Please check our paper for more results, including an ablation study of the various components of our method, results with more models, larger datasets, and a sensitivity analysis of the hyperparameters of our method. To know more about our paper, check out our project page using the link in this slide. Thank you.